Surfaces consisting of resin and paper have become a part of our everyday lives. Basic research has now produced new findings which describe the way in which these components behave during their production and processing phases. Based on these new findings, manufacturers and users of resin and paper now have a new basis on which to begin a mutually beneficial dialogue. At first glance, the basic manufacturing principle appears simple. Decor paper is processed by saturating paper with resin, followed by a drying step and hot pressing onto a suitable substrate. When combined, resin and paper create a substance which brings out the positive attributes of both components. This is accomplished in a way which enables the new product to satisfy the many special requirements which laminated surfaces must meet. Impregnating resin is composed of formaldehyde, water, melamine, or urea, as well as various additives. The depicted processes represent the production of melamine resin. A reactor is filled with the raw materials at room temperature. At the beginning of the resin manufacturing process, the mixture is heated to a set temperature which basically is maintained throughout the entire process. Formaldehyde reacts with melamine to create methylolmelamine, which during the condensation phase forms dimers and trimers. A ready-to-use impregnating resin consists of melamine, methylated melamine, and oligomeric compounds. As would be expected, the concentration of the individual compounds changes throughout the reaction. During the methylation phase, melamine and formaldehyde are linked to create methylolmelamine. In addition, methylolmelamine forms dimers and trimers. The duration of the condensation phase determines resin characteristics such as viscosity, reactivity, and shelf life. Measuring empirical solubility parameters such as water tolerance usually determines when the condensation phase has ended. The resin's positive attributes are not possible, however, without the introduction of a second component, the paper. Magnification shows the cross-section of a typical white decor paper, to which we now turn our attention. A white decor paper contains cellulose, water, and titanium dioxide as pigment. The weight distribution is as follows: 59% cellulose, 39% titanium dioxide pigment, 2% water, and a marginal amount of additives. However, when observing how the primary components are distributed by volume, we must also take air, or more appropriately stated, the microscopic gaps between the fibers into consideration. The size and distribution of these gaps can be controlled during the paper manufacturing, which has important consequences for the impregnation process. With the aid of this virtual impregnation treater, we will demonstrate a two-stage impregnation with urea in the first bath. At the first impregnation station, the core of the paper is filled with the resin solution. A pre-wetting roller applies the resin to one side of the web. The penetration itself occurs after the web has left the roller. The key phases of the impregnation process are wetting, absorption and swelling, penetration, and finally saturation. The surface pores are filled during the wetting phase. After 10 to 80 milliseconds, the resin solution has also seeped into the accessible pores. Water absorption causes the fibres to swell. At the end of this phase, approximately half of the pores are filled, and the absorption process slows down dramatically. After 100 milliseconds, the resin reaches the other surface, and after 400 milliseconds, the pores are approximately 80% full. After 2000 milliseconds, virtually all of the pores are saturated, although a small portion of pores remains vacuous. An additional surface coverage occurs during the following dip, but this resin does not penetrate into the paper. The paper is guided through the drying oven on a cushion of air. The web's temperature, however, does not exceed 100 degrees centigrade. Swirling hot air causes water to evaporate from the web, which reduces the resin volume. Air pockets are created inside the resin, but the paper thickness remains virtually unchanged. Surprisingly, the viscosity of the urea resin remains virtually consistent up to a volatile content of approximately 12%. Only when the residual moisture is less than 10%, an appreciable increase in the degree of cross-linking can be observed. This is why impregnates, as a rule, are not dried to a water content below 12%. After the web has cooled, gravier rollers apply melamine resin to both sides of the paper. At the interface, blending of the two resins takes place. During the second drying phase, the paper is also guided through the oven on a cushion of hot air. As this occurs, the melamine coating loses water until it contains about the same moisture level as is found in the impregnate's core. At the same time, the thickness of the melamine layer is also reduced considerably. The drying phase ends when the impregnate has reached a volatile content of between 5 and 8%. The viscosity of the melamine resin rises noticeably only when the volatile content is below 8%. As long as the volatile content remains above 3%, no significant cross-linking reactions will take place. Following the second drying phase, the core of the impregnated material has hardened for the most part, although the melamine surface remains flowable. The molecular distribution clearly shows that when paper is dried too far, the concentration of dimers and trimers, as well as the degree of cross-linking, vastly increase. In this case, the melamine resin is no longer flowable, and the impregnates are no longer usable. One could assume that once the core has been impregnated with pure urea resin, that melamine would only be found on the surface. In many instances, however, melamine is also found in the core following the second drying phase. After the web has left the second drying zone, it's cooled. At the end of the impregnation treater, the sheets are cut and stacked. The finished impregnate is laid onto a substrate, heated and laminated. The temperature curve at the interfaces between the press plate and the impregnate, between the impregnate and the particle board, and in the deeper layers, shows that the press plate's temperature is quickly transferred to the impregnate and the surface of the particle board. Only in some depth the temperature transfer is reduced. At the beginning of the lamination process, long, partially cross-linked structures are created from the oligomers. This so-called gelation marks the end of the flow phase. Additional molecular combinations create a three-dimensional network which gives the material its desired surface characteristics. Eventually, the chemical reaction comes to a halt. Usually, the reaction rate during lamination depends upon the temperature. Press temperatures above 130 degrees centigrade ensure a faster hardening process and a shorter flow phase. By examining the molecular changes, we clearly can distinguish between the flow and hardening phases. Initially, the portion of the oligomers, here displayed in green, rises rapidly, but it soon resides, giving way to cross-linked molecules. This maximum level marks the transition from a liquid resin to a thermoset. As the molecular structures change, so do their mechanical attributes. To begin with, we can examine a considerable softening of the resin in the flow phase. Afterwards, as the molecular cross-linking continues, we observe a rapid increase in the material's stiffness and hardness. This document